tablet, right?
Yes. Oldu.
Okay. Thanks for switching on the video, because in this way I feel less alone. And not only, your faces are useful, because my task is to try to teach you a practical capacity of doing some calculations. Consider that these calculations are not only calculations you can do with your pen on a sheet of paper or on a tablet. We can transform this into algorithms, and there are softwares like Mathematica, MATLAB, which are doing algebraic calculation automatically. So these kind of difficult calculations can be done also using computers. And so it is very important that you learn. In this part of my course this year, I'm following the strategy of my ancient professor in linear algebra. It is ancient because I'm talking about, I'm joking, 1979, when I started my studies, and the name of the professor was Franchetta. He was very clever and a very calm person. And the strategy was the following. He had one lecture. In the first third, he was repeating what he had said in the previous lecture. In the central third, he was telling something new. And in the last third, he announced what he was going to say in the next lecture. In this way, the students were hearing 3 times from 3 different points of view every subject. So the ideas were hammered in the head of students. Okay. So as you, the majority of students here want to do a master thesis and hopefully even a PhD with us, with my group, I think that you need to learn very well linear algebra and tensor algebra, because there is no physics without tensor algebra. Okay. Then it happens that I was pupil of the pupil of the pupil of Levi-Civita. So I belong to a school where tensor algebra is considered compulsory. Up to now, I did not manage to have any PhD student who really studied tensor calculus before PhD. So all the others, Ivan and Emilio, I was obliged to place a gun on the table and oblige them to study these things. I think that it is very useful for you if you learn what has been defined by somebody who was a little bit clever. His name was Einstein, as the most powerful mathematical tool for describing physical phenomena. Actually, he sent a letter to Levi-Civita, and I've seen this letter because I am a good friend of the grandson of Levi-Civita. In this letter, he wrote, "Without your tensor calculus, I could never invent relativity." Now, the truth is that without tensor calculus, you cannot invent any field theory. By the way, the reason for which I'm telling you that Piola was the founder of continuum mechanics is that in one of the next lectures, I will tell you how Piola started the Italian tradition arriving up to Levi-Civita. So the motivation which pushed Levi-Civita to develop tensor calculus originated from continuum mechanics. So continuum mechanics needed tensor calculus for being developed, and we needed to wait around 100 years before the tools of tensor calculus were ready, and only after tensor calculus had been developed, continuum mechanics became usable with numerical computations for designing bodies which are deforming. Okay, so you know, usually mathematics is like that. You have continuum mechanics. It requires a mathematical tool, and then you develop tensor calculus. Then, thanks to tensor calculus, you invent relativity. So it is a kind of interaction which you know, starts with a mathematical model of reality. So here you have physics, so you have phenomena. The theory of the deformable body required the invention of continuum mechanics. Then continuum mechanics urged mathematicians to invent tensor calculus, and then tensor calculus was used for studying relativity. So the interplay between mathematical modeling of physical phenomena and mathematics is very important for both. Okay, now this is a motivation, and let's now go slowly to continue the calculations which we started yesterday. Erden, I see you finally.
Hi, Professor.
Okay.
Buongiorno.
Okay. Buongiorno. Okay, so we can start with a vector space. Okay, so we have only the structure of vector spaces. Okay. Dimension of V is equal to n. So you can find E1, E2, En. Okay, let me use the B here because I want to call vectors with capital letters. So we have n vectors, and these vectors are linearly independent. What it means linearly independent? That for every alpha 1, alpha 2, alpha n, you have summation over I of alpha I of EI equals 0 implies for every I, alpha I equals 0. So the only linear combination of a set of linearly independent set of vectors which produces the vector 0 can be obtained with all coefficients equal to 0. I think that you have met this definition many times. If you have troubles, go back to read this part of linear algebra. E1, E2, En is a basis. Why? Because when for every V belonging to VB, there exists a unique n-tuple Vi belonging to Rn such that V is equal summation over I of Vi EI. Okay. Okay. I already was a little bit not precise. Why? Because I want to follow Einstein convention. And whenever I have an index on which you have summation, I want to write one of these indexes up and the other of these indexes down. Okay. Now on, I want to repeat for you that this means alpha 1 E1 plus alpha 2 E2 plus alpha n En. This is a quick way for writing this. Okay. And as we are, like Einstein, very lazy, we write alpha I EI, even forgetting about the symbol of summation. Okay. So whenever you see two indices, one up and one down, repeated, I mean that the summation is intended. Okay. So we have the vector space VB. Okay. We have a basis E1, En, or if we want to do it quicker, EI. So we know that every V belonging to our space VB can be written like Vi EI in a unique way. The definition of linearly independent set of vectors is what? You can represent zero only with zero coefficients. Okay. And this implies that you can represent every vector in a unique way with its coordinates. These are the coordinates. Okay. Of course, like my professor Franchetta was repeating every day, if you change the basis, you change the coefficients. So if you have another basis, so instead of using E1, En, you use E prime 1, E prime n, another basis, you will have other coefficients, V prime I, E prime I. And you can remember these because you know already these things. If you have this vector here and you use the basis which I have drawn there, the components of these vectors are beautiful. This is an example. I am talking about a particular vector space. Which one? E2, the set of arrows in the plane. Okay, and I'm considering it as an example for telling you something which is more general, and it is valid in every vector space. If instead of, so to this arrow blue, which I have drawn on my tablet, you associate this coordinate, so the length of this segment, and this coordinate, the length of this other segment. If you use these other bases, then you will get two different numbers, this length and this length. So the coordinates change when you change basis. Okay. So tensor calculus can be said, can be called in this way. Tensor calculus is the science of the variation of physical quantities when you change the basis. Okay. I mean, this, of course, is not a formal definition. It is an informal motivation of what we are doing. Okay, so we must be aware of the fact that when you change the basis, the coordinates of a vector are changing. And we are strongly interested in understanding how coordinates are changing as a consequence of the change of the basis. Okay. Now, yesterday, we introduced the dual of the vector space VB, and this dual is usually called V star B. V star B is the set of linear maps defined in VB having values in R. Now, somebody could ask me why you have, usually engineers and engineering students, when you oblige them to study some new mathematical idea, they ask you, why you are doing this? Why I must suffer for understanding this new concept? Is it really necessary? Some years ago, a nice girl student came to see me, very elegant. She prepared in a very elegant way to come to me and telling me that she had asked around, and somebody had told her that in modern times, linear algebra is not useful for engineers. It is like the typing machine, you know, the one which I was using when I was young, you know, for writing documents. Something obsolete. Okay, my dear friends, linear algebra, I am afraid, will never become obsolete. I don't know. It could be they invent another theory, but there is no code in our computer which is not using systematically linear algebra. You know, MATLAB. Do you know what it means? Matrix laboratory. So we cannot survive if we don't understand linear algebra. Okay? But this is a statement like asking you to believe what an old man is telling you. So in the last lecture, I reminded you something. The concept of power, of a force on a velocity, which is a physical concept which you have for sure studied. So they defined for you F dot V, where F is a force and V is a velocity. Okay. What is this? This is a linear function which depends on F in the set of velocities. And velocities belong to a vector space. So actually, if you want to talk about the power of forces, you must talk about linear maps defined in a vector space. So let us close this bracket because you should not be disturbed by particular cases. Okay, you should not be disturbed by examples. Let us remain in the abstract, in the abstraction of general definitions, because in this way your tools will be applicable in a wider set of situations. So what we have the vector space VB, and we have a basis EI, and then we have the vector space VB star, and you have the basis, wait a second, and you have defined it as the set of linear applications defined in VB with values in R. Okay. We know that the dimension of VB is n. The dimension of a vector space is the number of vectors which are forming a basis. Okay. A basic theorem in linear algebra says that if I have the basis EI and the basis E prime I, okay, the cardinality, which means the number of objects in the set of EI, is equal to the cardinality of E prime J. What it means? In the space of vectors of arrows, you cannot find a basis of 3 vectors and a basis of 4 vectors. In a given vector space, the number of vectors in a basis is fixed. And this is the dimension of the vector space. Okay. I'm sure that you have proven this in your linear algebra, maybe courses, maybe you have forgotten it, but this is rather natural. This is the reason for which we are talking about three-dimensional Euclidean space or n-dimensional vector space. You must accept that when you need 3 vectors for representing every displacement, you cannot be clever and with 2 vectors you can represent every displacement, or you cannot find 4 independent vectors which form a basis of the 3-dimensional space. The basis of a 3-dimensional space is always made by 3 elements. Okay, so this is something which should be rather clear. Okay, now the question is, can we say something about the dimension of V star B? Yesterday, we have, first of all, remarked that V star B is a vector space. Okay. We know this why, because we introduce, if we have L1 belonging to V star B and L2 belonging to V star B, we can define L1 plus L2. How? This definition is useful because you must understand what we are doing. L1 plus L2 must be an element of V star B. Okay? So it has to be a mapping which maps vectors into real numbers. So which is the real number as to V, capital V, by the linear application L1 plus L2? L1 plus L2 applied to V is equal to L1V plus L2V. This is a definition. So on the left side, when I place 2 dots on the left, it means that the object on the left is defined by the object on the right. This we know already. This is a real number. This is a real number. We can sum 2 real numbers. So everything on the right side is known. And the new object on the left is defined by this equality. So this is a definition. Okay. Next step, alpha L1 applied to V is by definition equal to alpha L1 of V. Okay. So V star B has a sum and has a product times a scalar number. We must verify the axioms of vector spaces. Okay, you can do it. Go read, you find it also in Wikipedia, you discover, for instance, that the null vector in V star B is the application which maps to every V 0. This belongs to the real numbers. It is a little bit confusing. One should use different symbols. This belongs to V star B, and this belongs to the real numbers. So the 0 in the dual space V star B is the vector, the application, which maps to every vector the real number 0. So it is the constant function mapping every vector into 0. Okay. Given a vector, an element L in V star B, minus 1L plus L is equal to 0. Okay, so this means that you have the opposite of every element of V star B. Okay, so V star B is a vector space. Of course, this is a vector space built VB. You have defined it starting from VB. So now the question is, dimension of VB equal n implies something about the dimensionality of V star B? Okay, I started proving, but we will do everything again now, that if VB is finite dimensional, then V star B is finite dimensional, and the dimension is the same. Okay. Look, you will never understand what is a force if you do not understand V star B. Okay? So if you want a strong motivation for continuing now is that, I mean, and this is not what I said, okay? This is clear in Levi-Civita book. Since Levi-Civita introduced the concept of dual of a vector space, everything was clarified in the field of, in many parts of mechanics. Okay, but we will discuss this deeply later. We need to have the tools. Okay, so we start introducing L-I-E-I. This is a long notation. We will change. Let's call it LJ-EI. This is a linear mapping from VB into R. Okay, you forgive me. I will not write all the time this. LJ means that you have already specified the basis. Okay. Lj of a vector V is equal to the component J of V in the basis EI. Okay, so V is equal Vj, Ej, okay, and you pick exactly the jth component. Okay, why I'm changing the index I into the index j? Because you must understand that this equality, this equality, this equality are all the same. Because what this means, take j equal 1 and write v1 e1. Take j equal 2, write v2 e2. Take j equal n, write vn en, then sum all these products. If instead of calling the dummy index j, I call the dummy index I, is changing the final result? It isn't. If I call the dummy index h, is it changing the final result? No, it isn't. So these formulas are all equivalent. By the way, if you have written a code in every computer language, I'm sure you have met the command do for I equal 1 n, and then you have a loop until you have end at the end of the command. And you know that if instead of calling I the index, you call it h, or however you call the index, the final result is the same. So you are familiar with this situation. So instead of telling you that L1 V is equal to V1, L2V is equal to V2, Ln V is equal Vn, I am bored. I do not want to write all these formulas. I write L I V is equal VE. Being a pupil, a grand pupil of Levi-Civita, I changed the index even without thinking. Okay. So what I have invented L1, L2, Ln. So these are n elements of V star B. Okay. Another thing that every pupil of Levi-Civita is doing is calling always vectors. I call vectors the elements of a vector space. This is misleading, so I will try to avoid to do this, but be ready to this confusion. So you have VB, and you have the vectors in VB. Then you have V star B, which is the set of linear applications defined on VB in the set of real numbers, but this is a vector space, and this is a vector space. Don't be confused. They are not the same object. Okay, so in this room we have Nurettin and Bekir. Okay, so Nurettin and Bekir are human beings from Turkey. Okay, So when I say human being from Turkey, I mean also Erden. Okay? I mean many other things. So when I'm talking about vector space, I mean a general concept. VB is a particular example of the concept of vector space, and V star B is another particular element of example of a vector space. Okay? Very well. So I have L1, L2, Ln. And now I ask myself, are forming a linearly independent set of vectors? Are they forming a linearly independent set of vectors? Why? Because I want to prove that they are a basis for V star B. Okay, so the first move is to prove that they form a set of linearly independent vectors. So I write alpha 1 L1 plus alpha 2 L2 plus alpha n Ln equal to 0. Of course, this is an element of V star B. Or if you like, alpha j Lj equal 0. Okay? Very well. Now, what this means? This is equivalent to say that for every V, alpha j Ljv is equal to 0. Now, this 0 is an element of V star B. This 0 is a real number. Okay. Now, what is Liv? By definition, for every V, alpha j Vj is equal to 0. Now, remark that Lj depends on the basis EI, and these are the components of V in the basis EI. Okay, so this formula is basis dependent. Okay. Okay. So I can choose. Now, the reasoning which we will do now, the reasoning which we are doing now, which we are doing now, is a basic reasoning in continuum mechanics. So what I want to say is that we will write many times this formula where V means something, physically meaning a quantity, and alpha means something else. Okay. So This is a reasoning which you should learn, because otherwise you will never be able to proceed in what we are doing. So we have that alpha 1 v1 plus alpha 2 v2 plus alpha n vn is equal to 0 for every v1, v2, vn. Now, v1, v2, vn are the components of a vector. So this is an element of Rn. Okay? So let us study the case n equal 1. So you have for every v1, alpha 1 v1 is equal to 0. I hope that you don't have doubts. If I have a number alpha, which multiplied times every real number gives you always 0, then alpha 1 is equal to 0. The only real number which multiplied times every other real number gives 0 is the number 0. So, you know, I know that this is people usually think that either I am crazy because I'm telling very stupid things, obvious things, or I'm crazy because I am making complicated reasonings for telling something very easy. But you know, if you have 0 times x and you get always 0, this means that 1 over 0 is meaningless. Because there is 1 over 0 should be the solution of this equation. And this equation has no solution. You cannot do any numerical computation, seriously, if you don't know that this is meaningless. Because very often, in some algorithms, you get that a quantity becomes 0 and this quantity is under a division sign. Okay. This is another experience I had with my students in the past years. A student came to me and told me, be quick, tell me in 2 words why 1 cannot divide by 0. Okay, so I answered that I cannot divide by 0 is 4 words, and so I cannot tell it in 2 words. The whole algebra of real numbers is behind this. So I hope that you are familiar with this, because otherwise we may need 40 hours of a class for understanding this. By the way, I hope that Alessandro, Ivan, Erden will help you with suitable readings if you have doubts, if you are afraid to ask. You know, so you may think that I am a bad person eating students who do not know something. Okay, ask Erden or Ivan or Alessandro. They will give you all books and you will rediscover easily these kind of things. Okay. Okay, let's go ahead. You know, I'm investing a lot of time in this subject because in my 29 years of teaching, I have discovered that this is the most difficult concept in continuum mechanics. I mean, students become crazy for this. So it is better if we start telling since the very beginning. Okay, now we have n generic. If we have n generic, we have alpha 1 V1, alpha 2, V2, alpha n, Vn. This has to be equal to 0 for every V. So if something, now we are talking about Aristotle logics. If every man has two eyes, then has two eyes. Let us pull Erden's leg a little bit. He knows me very well, so I can pull his leg. If I pull the leg of somebody else, he can be very upset. But Erden knows me rather well. Okay, let us admit that Erden is a human being. Okay, if he's a human being, and if it is true that every human being has two eyes, then Erden has two eyes. Okay, so if this number is 0 for every V, then this number is 0 for a particular vector V. Okay? So I am free to choose V1 equals 0, equal 1, V2 equals 0, Vn equals 0. I can do this. If this is true for every V, then this is true for this particular V. I write the equation, and what I write? Alpha 1, 1, plus alpha 2, 0, plus alpha n, 0, equal 0. These are all zeros, and I get alpha 1 equals 0. Wonderful. If I choose V1 equal 0, V2 equal 1, V3 equals 0, Vn equals 0, you are clever boys. Alpha 1 dot 0 plus alpha 2 times 1 plus alpha n times 0 equals 0. And this implies that alpha 2 is equal to 0. I can repeat this for every n. So I get as a result that this implies for every I, alpha I equals 0. And this means, coming back to our starting statement, that for every V, this quantity is equal to 0 implies that for every J, alpha J is equal to 0. So the set of Li's, which we had at the very beginning, is a set of linearly independent, vectors. Okay. Okay. Before we go ahead, I want to repeat this reasoning using a compact notation. So for every V, alpha J Vj is equal to 0. Okay. Then I choose Vj equal delta JH. You know, this formula tells you when H is equal to 1, you remember what is delta? Delta IH is 1 when the indices are equal, and it is 0 when J is different from H. Okay. So writing this formula here, I am quickly writing this these, and all the others. So look how quick becomes my calculation, and I'm writing exactly the same thing. But instead of writing pages and pages of calculations, I have written a very short formula. Now, my dear friends, the poor Piola wrote this kind of formulas here. He could not use the tensor calculus. So he needed hundreds of pages of calculations. I have translated Piola from Italian into English, word by word. Then, having the English translation word by word, I simply used the modern notation of Levi-Civita. The original pages in Italian are 400. Italian is a heavy language. If you will learn Italian, you will discover how elegant it is, but also how heavy it is. It is complicated. I don't know Turkish, maybe it is also, but Italian is rather complicated. 400 pages of Italian become 300 pages in English. Okay? Then I use Levi-Civita notation, and I wrote 50 pages. Formulas nearly disappeared, but we meant exactly the same thing. I will say more. Using Levi-Civita formulas, using this notation, then you can tell to a computer what he has to do. So this is also more powerful. So Piola versus Levi-Civita. Okay. So let us continue this reasoning here. I have delta J H. Okay, look, when I am wrong, I get immediately, while writing the formulas, I get immediately an information on where I should write the indices. You see? You will see now why I need this. So you have the delta JH alpha J equals 0. Okay. And this means that as this delta is 1 only when J is equal to H, this implies alpha H equals 0. And as H is arbitrary, using Levi-Civita notation, in 3 lines, I have proven the same result quickly. Okay? So we will keep doing these calculations in 2 different ways for a while, because you must learn how to become master of this process. Okay. Now we have found that Lj gives you a basis. No, we don't know it is a basis. A set of linearly independent vectors. Okay. So dimension of V star B is greater or equal to n. Because you have found inside V star B n vectors which are linear independent. Okay. Now we will prove, we did already in the last lecture, but we repeat it now, that dimension of V star B is smaller or equal than n. So at the end, we prove that the dimension of V star B is exactly n. Okay. So how we do it? We consider a L belonging to V star B. Okay. And we prove that L is a linear combination of Lj. And if we have proven this, we have proven that the dimension of V star B is smaller or equal than n. Okay. So what I do, L star, L belonging in V star B, I calculate it in the vector V. This is an element of VB. Okay. So what I do, this is equal to L VI EI. Okay. As L is linear, I can write VI L EI. But by definition, VI is equal to LIV. So I can write this equation. Okay. So let us see what L of V is equal to L EI Li of V. So L is equal to L EI Li. This is a real number. This is an element of V star B. Okay. So what we have proven, that this is the component of L in the basis Li. So if you have the linear mapping L, okay, and you want to represent it in the basis Li, so if you want to find the component of L in the basis Li, you must calculate L on EI on the basis you have at the beginning. Okay. So let us resume what we have done. Remark. We did this without talking about inner product. You know, this is typical of any mathematical reasoning. When you prove something, you must prove it with the minimum possible hypothesis. So we have proven that the dimension of V star is equal to the dimension of V without using the fact that in this vector space we may have or not an inner product. Okay, so this is essential in our reasonings. Okay, so we must have clear that this identification is not an identification. These results, this proof that the dimension of V star B is equal to the dimension of VB does not depend on the inner product. Okay? And we will introduce inner product later. Okay, so we have VB. We have EI basis of VB. Then we have V star B. And now we have introduced Li. Now, Li, you remember, it depends on EJ. You have defined Li of V, Li of V is equal to the component Vi of V in the given basis. Okay, so Li depends on the basis EI. In order to remember this, to keep this dependence clear in the notation, without writing this clumsy, heavy notation, Levi Civita proposes to call this EI with the I at the top. So this EI with the I, so when we write EI, we mean Li related to EJ basis. Okay? So this is a co-basis of V star B. Co-basis is, it means co-basis with respect to EI law. So now you must always keep in your mind this fact. VB EI, V star B EI at the top. And when you choose these, then you have blocked this other one. So you are free to change only this basis here. Then everything happens as a consequence. Okay, you change these bases, and as a consequence, you change also the basis of V star B. Okay, now we have only 14 minutes. So let us start telling more quickly something which we will do in the next lecture. We must change EI. So we must change the basis. So what we do? We introduce E prime J. This is a set of vectors, set of linearly independent vectors. How many? J goes from 1 to n. So we have another basis. Okay. Now, E prime J is a vector, is a particular vector. So I can write it as a linear combination in terms of EI. Okay. Now, the coefficients of this linear combination need two indices. One index refers to this, and the other index refers to this. So I know that here you have sum over I, no sum over J, obviously. So let us write this once more without indices. I have E1 prime, the new, the first vector of the new basis. This is equal to L1, 1E1 plus L1, 2E2 plus Ln 1En. So you remark that I can use the Einstein notation in this way for saving this complex sum. Okay. Then I can write E prime 2 equal, and I will write Li 2 EI. And then E prime n equal Li EIN. Okay. I am bored. I do not want to write all these formulas. So I also use an index for this. So I write E prime J equal Li J EI. Okay. Now, let us try to understand something. This is an index running with the basis, the old basis. And this is an index running for the new basis. We will need soon to make a lot of calculations. And we risk to lose the information which index refers to which basis. You understand this, right? So, following Einstein, this is a novelty of the notation introduced also by Einstein. We will write J prime with the same index, the same symbol for the new basis. So the index relative to the basis E prime takes a prime, and the index relative to the old basis has no prime on it. Okay? So in a way, we invent a notation for the indices which relates the index, relates each index with the corresponding basis. Okay. So this is essential for what we will do in the following. Okay. So L I J prime is the transformation let's call it matrix from EI to E prime J. So E prime J, the generic new vector in the new basis is equal to Lji EI. Look how elegant is, and now I place G prime, G prime. How elegant is this up and down convention? On the left and on the right side of every equation, you must have the same number of free indices up and down. So if you have a free down index on the left, you must have it free. Free means without another one repeated on the right. And if in your calculations this goes up, something is wrong. You must have the same localization of indices on both sides of any equation. Erdan, tell me, are in Berkeley teaching you these things, or they are not good enough?
No, they are teaching this stuff.
Okay, so they keep doing these things.
I can share you the lecture notes if you want.
No, thanks. No, I won't. We need to write some lecture notes on this. Okay. But they are doing exactly in this way, right?
Yes.
So the tradition of Levi-Civita reached also Berkeley.
Yeah.
Levi-Civita was rather clever. He wrote in French, and then he paid somebody with a master in mathematics to translate his book in English. And then he obliged the University of Rome to send a copy of his book to every library in the world. So they could not pretend they didn't know it. It was rather clever. Okay, now what we will do next time. Given Lij prime, we will see how components of vectors are changing. And also, by the way, maybe I didn't tell you, V star B, an element of V star B, is called covector. Okay. So we will see how components of vector are changing, but also how covectors components are changing. Okay, this we will do in the next lecture. Okay. Okay, so we will talk about how to organize our future lecture. So first of all, next Monday, you confirm that I can continue until 11, right?
Yes, Professor.
Okay, and then we need to recover 1 hour a week plus the 4 hours or maybe 6 hours, which we have lost up to now. We will decide how we can do it, okay? Erden, be careful. Stay far from Cardillo. Don't infect him.
Okay.
You must wait 2 weeks before kissing an Italian girl,
Okay.
So don't go another time in the center of the village chasing the girls, okay?
Okay.
Okay. So we will. I will call you in the next. I hope today or tomorrow. Then, okay.
Okay. See you.
Bye bye. See you everyone.